Greetings, I am 3STEM. I hope you are all hanging in there even after the extension of the shelter in place has been made to add another month. The good news is that the state is allowing some loosening of the order on some businesses. Construction workers are able to get back to building things and more places are being deemed essential. Maybe we'll be able to get a haircut someday soon. The first lesson on the topic of sequences and series was full of new notations and ideas around sequences and series. I reminded you about arithmetic sequences and how to find the nth term either through the explicit formula or through a recursive one. And today we're going to be focusing on the geometric sequences and their related formulas, as well as talking about geometric series. As I mentioned before, getting more familiar with working with these sequences and series will be helpful when you have to work with them in calculus. So let's go ahead and move ahead here. In geometric sequences and series, we were talking about arithmetic series sequences before and how they are separated by a common difference. Here, we're going to be talking about geometric sequences and how geometric sequences don't have a common difference, but they do have something called a common ratio. So if you remember then, the definition of a geometric sequence is A1, comma A2, comma A3 in such a way that if I took A2 and divided it by A1, or A3 and divided it by A2, and A4 and divided it by A3, I will get something called a common ratio, which is meaning that we are now multiplying instead of adding. So here are examples of geometric sequences. The sequence whose nth term is 2 to the n is geometric. For this sequence, the common ratio of the consecutive terms is 2. So it starts with 2, so A1 is 2, and we multiply that and get 4, and multiply that and get 8, etc., etc. And so that's what's going on when n is equal to 1, meaning the first term is 2. The sequence whose nth term is 4 times 3 to the n is geometric. For this sequence, the common ratio of consecutive terms is 3. So notice the first term is 3 to the 1 times 4 is 12. And 3 to the 2, which is 9, times 4 is 36. And once again, n, the first occurrence of n, is when it's equal to 1. So further, the sequence whose nth term is negative 1/3 raised to the nth power is geometric. For this sequence, the common ratio of the consecutive term is negative 1/3. So watch how this one works. Negative 1/3 is the first term, and that happens because we begin with n equals 1, so n equaling 1, negative 1/3 to the 1 power is negative 1/3. But when we multiply negative 1/3 times negative 1/3, negative times negative is positive, and we end up with 1/9. So the next term is going to be negative then, 1 over 27. And notice that we have this oscillation of the sign from negative to positive and so forth. So here's something that looks like a sequence that is a sequence because it has a rule, but it's not a geometric sequence. So notice 1, 4, 9, 16, whose nth term is n to the 2. Notice that it's not geometric. And the reason why is because the ratio of the second term to the first term is 4 over 1, but the ratio of the third term to the second term is A3 over A2 is equal to 9/4, which is not the same as 4 over 1. So we don't have a geometric sequence because we don't have a common ratio. But it's a sequence nonetheless. Now let's go back to geometric sequences and talk about the nth term of a geometric sequence. The nth term of a geometric sequence has the form a sub n is equal to a1, which is the first term, times r, which is the common ratio, raised to the n minus 1 power. So r is the common ratio, and so every geometric sequence can be written in the following form then. A1 times r, a1 times r squared, a1 times r to the third, and a1 times r to the fourth, and so on. Recursively, we can say we can find an if we knew what an minus 1 is by saying an minus 1 times r and get an, or we can say an plus 1 if we know what an is. And so an times r becomes an plus 1. So find the terms of a geometric sequence. So this is example 2 in the book. Write the first 5 terms of the geometric sequence whose first term is 3. So a1 is 3, and whose common ratio is 2. So we know that if we take a1 and times r to the n minus 1, that's really the nth term of the sequence. And so let's just go ahead and apply this. We want to know what a1 is, and that's going to be a1, which is 3, times r to the 0 power. But r is 2, so 2 to the 0 power, that's just 1, and so a1 is 3. a2 is going to be 3 times 2 to the 1, because 2 minus 1 is 1, and so 2 to the 1 is 2. 3 times 2 then is 6. a3, 3 times 2 squared, 4 times 3 is 12. a4, 3 times 2 to the third, 2 to the third is 8, 8 times 3 is 24. And we're trying to find the first 5 terms, so a5 is 3 times 2 to the 4. That's going to be 3 times 16, that's 48. Let's plot the points of this sequence. So I'm going to go ahead and put 10, 20, 30, and 40, and mark that as the a sub n values. This is going to be the n values, 1, 2, 3, 4, and 5. So when n is equal to 1, a sub n is equal to 3. That puts a point about right there. When n is 2, a sub n is 6. That puts us about right there. When n is 3, a sub 3 is 12. That puts us about there. And when n is 4, we're at 24. So 24 is about right here now. And we're at 5, we're off the chart and up about there. So if I tried to graph that, it starts to look almost exponential. Here we find in example 3, we're asked to find the 15th term of the geometric sequence whose first term is 20, a sub 1 is equal to 20, and whose common ratio is 1.05. So r is 1.05, and a sub 1 is 20. So when we start to write our nth term, we're going to say a sub n then is equal to 20 times 1.05 raised to the n minus 1 power. So we want to know what the 15th term is. So this is going to be a sub 15. That's equal to 20 times 1.05 to the 15 minus 1 power, or 20 times 1.05 to the 14th. So if I raise 1.05 on a calculator to the 14th power, I get 1.9799. And if I multiply that by 20, I get 39.599. And that's approximated. So there's my a sub 15 found on a calculator. In example 4, we're being asked to find a term of a geometric sequence. So this one's saying find the 12th term of the geometric sequence if, and notice a sub 1 is 5. So if I took 15 and divide it by 5, because that's the second term, divide by the first term, and I get 3. And let's see if that happens again. 45 divided by 15 is also 3, so we're good. We have an r then of 3. So we can say a sub n is equal to 5 times 3 raised to the n minus 1 power. And so we want to know what the 12th term is, so that's going to say a sub 12 is going to be 5 times 3 to the 12 minus 1, or 5 times 3 to the 11th. So 5 times 3 to the 11th, pick up a calculator again, and 3 to the 11th power is 177,147. 5 times that, 885735. So 885,735 is a sub 12. Now we're being asked to find a specific term of a geometric sequence. The 4th term of the sequence is 125, so we can say a sub 4 is 125. And a sub 10, the 10th term, is 125 over 64. So that's a sub 10. Find the 14th. So we want to know what a sub 14 is. Well, let's figure that out. Assume the terms of the sequence are positive. Well, we know that a sub n is always equal to a sub 1, which we don't know, times the common ratio, which we also don't know, but that times n minus 1. So we know that a sub 4 then can be written this way. A sub 1 times r to the 3, because that's 4 minus 1. And we also know that that's equal to 125. We also know that a sub 10 is equal to a sub 1 times r to the 9th. And that's equal to 125 over 64. And we should also go like this. We should say a sub 1 r to the 9th divided by a sub 1 r to the 3. A sub 1's will cancel each other, and we'll figure out what r to the 6th is. So that's 125 64ths divided by 125 over 1. 125's cancel in that case right there, and that's just 1/64 over 1. So r sub 6 then is equal to 1 over 64. 2 to the 6 is 64, so we could actually rewrite this as 1 over 2 to the 6th power, which is r to the 6th. So if I took the 6th root of both sides, I end up with r is equal to 1 over 2. So if r is equal to 1 over 2, that's a nice thing. We can actually say a sub 1 times 1/2 to the 3rd power is equal to 125. So that's the same as saying a sub 1 times 1/8 is equal to 125. And we multiply both sides by 8, and we get a sub 1 is equal to 1,000. So a sub 1 is equal to 1,000, and r is equal to 1/2. So we can actually write a sub n then is equal to 1,000 times 1/2 raised to the n minus 1. So a sub 14 then is going to be 1,000 times 1/2 raised to the 13th power. Pick up a calculator, 1 divided by 2, take that answer and raise it to the 13th power, and multiply that by 1,000. And we get 0.1221. And there it is. Now, the next important thing to talk about here is the sum of a finite geometric sequence. This is meaning I'm wanting to add together all of the terms of a sequence from the first term through the, say, 15th term. And that would be finite because it's only the first 15 terms and not all infinity terms of the geometric sequence. If we talk about it that way, notice that the first term, a sub 1, is just a sub 1. And so the second term then becomes a sub 1 times r, and the third term becomes a sub 1 r to the 2, and on and on and on, so that the nth term is a sub 1 r to the n minus 1. Now, if we took that and instead of putting commas in there representing it as a sequence, we want to represent it now as a series, and this is called a finite series, where s sub n is equal to a sub 1 plus a sub 1 times r plus a sub 1 times r to the 2 plus a sub 1 r to the 3, and on and on and on to finally say plus a sub 1 r to the n minus 1. S sub n now is equal to the summation as I starts to be 1 and raises to n, a sub 1 r to the I minus 1 is equal to now a sub 1 times 1 minus r to the n over 1 minus r. Proving the formula for the sum of a finite geometric series is actually rather simple. You see, we can take S sub n and write it out as a sub 1 plus a sub 1 times r plus a sub 1 r to the 2 plus a sub 1 r to the 3 plus dot 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 plus a sub 1 r to the n minus 2 plus a sub 1 r to the n minus 1. And then we can take another copy of that and say, let's multiply all terms by r. Then I would have r times s sub n, and that would be a sub 1 r plus a sub 1 r to the 2 plus a sub 1 r to the 3, and on and on and on until I got to plus a sub 1 r to the n minus 2 plus a sub 1 r to the n minus 1 and a sub 1 r to the n. So if I subtract s sub n minus r times s sub n, I end up with this, that the terms from s sub n actually subtract the terms from r s sub n, at least in the middle parts, and leaves behind a sub 1 minus a sub 1 r to the n. So if I factor out s sub n, I get s sub n times 1 minus r, and that's equal to a sub 1, if I factor that out, 1 minus r to the n. So dividing both sides by 1 minus r gives me now that s sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. In example 6, we find the sum of a finite geometric sequence here. This one starts with n is equal to 1 and goes to n is equal to 12 and is 4 times 0.3 raised to the n power. So we need to find what the first term is. The first term is going to be when n is equal to 1, so that's just 4 times 0.3, that's 1.2. And then we also need to know a sub 12. So a sub 12 is going to be 4 times 0.3 raised to the 12th power. Now that is 0.3 raised to the 12th power times 4, 2.1258 times 10 to the negative 6, and that's a sub 12. We take our sum formula, s sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. We know that r is 0.3. Let's just plug in the pieces now. S sub 12 is equal to a sub 1, which is 1.2, times 1 minus 0.3 to the 12th power over 1 minus r, which is 0.3. So if we punch that all into the calculator, and my answer is 1.7143. So that's the sum of the first 12 terms of that sequence. Something which you need to be aware. When using a formula for the sum of a geometric sequence, you need to be careful to check that the index begins with I equals 1. If the index begins I equals 0, you must adjust the formula for the nth partial sum. For instance, if the index in the previous example had begun with n equals 0, then the sum would have been, now look carefully, the sum where the index is n equals 0 and goes to 12. And so look at the first term there now. We have to the 0th power is what you need to do. And then this is the guy that we solved in the previous example. So that 0th term, since 0.3 to the 0 power is 1 and that times 4, there's our first term of the sum. And then the rest then is added to it that we had solved in the previous example. So in the topic of geometric sequences, because of the multiplication, we have a special circumstance that applies to geometric series. The summation of the terms of an infinite geometric sequence is called an infinite geometric series, or simply a geometric series. The formula for the sum of a finite geometric sequence can, depending on the value of r, be extended to produce a formula for the sum of an infinite geometric series. Specifically, if the common ratio r has the property that the absolute value of r is less than 1, it can be shown that r to the n becomes arbitrarily close to 0 as n increases without bound. So let's take a look at this. We just developed the formula for a finite geometric series, and in such a way that 1 minus r to the n is in the numerator of that formula. So we have a sub 1 times 1 minus r to the n over 1 minus r. But notice here, we let r to the n now become 0 as n goes arbitrarily close to infinity. Now we have a sub 1 times 1 over 1 minus r. As we get into talking about example 7, which is find the sum of an infinite geometric series, we need to remind ourselves what is the formula for the sum of an infinite geometric series. And as we write it in sigma notation, we remind ourselves that the index is I is equal to 0, and we're going all the way to infinity of a sub 1 times r to the I. And when we have that, we get that a sub 1 over 1 minus r is that sum of an infinite geometric series. Now, look at the difference between what we have there and what we have in part A of example 7. We're given sigma notation, but we're given an index of n equals 1. But the formula there has n minus 1 in the exponent of r. So we actually have exactly the same thing. You see, if we let I equal n minus 1, then we have exactly what we want. Now we can replace the n minus 1 with I equals 0, and we can replace the n minus 1 with I. We have exactly what we're looking for. And so we could just go like this. We know what a sub 1 is, that's going to be 4. And we know what 1 minus r is, that's 1 minus 0.6. So look at what this becomes. 4 divided by 0.4. And that's equal to 10. So as we're getting into part B, I'm wanting you to notice that the first term is 3. That's your a sub 1. Now, we're taking a sub 1 and multiplying that by 1/10 to get 0.3, and then 1/10 squared to get 0.03, and on so on. So r is then 1/10. So we can take our formula now and just say a sub 1, which is 3, and divide that by 1 minus 1/10. Well, that's equal to 3 over 0.9. And that reduces to 10 over 3, which is 3.333, and on and on and on. As we get into talking about example 8 called increasing annuity, you may ask the question, when am I ever going to use this kind of math in real life? If you become an actuary or a broker for retirement investments, you may actually see a problem just like this. So a deposit of $50 is made on the first day of each month in a savings account that pays 6% compounded monthly. What is the balance at the end of 2 years? This type of savings plan is called increasing annuity. So if you really look at this, and you start with talking about the very first of your $50 investments, just talk about that first one. So we're just going to say first, then we're going to say it this way, that one is actually going to increase for the full 24 months or 2 years, right? So we have $50 is my investment right there, and that's going to increase using compounded interest, 0.06 for 6% over 12 months in a year for monthly, and then that times 2, which is 2 years, times 12. And so there that is. So look at what we have. We have $50 times, and this comes out to be 1.005 raised to the 24th power. So the second investment then that you make is going to do pretty much exactly the same, only it's going to do it for 23 months because you waited for the second month in order to do it. So this one's going to look like this. 50 times 1.005 to the 23rd power. Now, if you think about that and go all the way to the last investment that you make, so here's the last investment. That one's only going to gain interest for 1 month. So the interest for that one and what you have from that investment is this, 50 times 1.005 to the 1. So I hope by now that this is clear to you that your a sub 1 is this value right here, and that r is equal to 1.005. So what we're going to do then is use the formula for the sum of a finite geometric series. And so we're going to do that. So S sub 24 then is going to be a sub 1, which is 50 times 1.005, and that times 1 minus r, which is 1.005 to the nth power, which is 24. And that divided by 1 minus r, which is 1.005. Now, if you put that all together, it comes out to be, on a calculator, $1,277.96. So by investing $50 a month for 2 years, you end up with $1,277.96. And so there you have it. That is section 11.3, the sequences and series that are geometric. And so the homework that we have for you is on page 828, problems 1 through 37, every other odd, 51 through 91, every other odd, and 99 and 101. That's 23 problems in all. If you have questions on how to do any one of these problems, feel free to stop in on my study hall or give me an email, and we can schedule a time that we can meet and talk about your questions. All right, talk to you later.